Collision theory is the best way that we have come up with to explain how reactions happen. Basically, in collision theory, the chemicals have to collide with one another with enough energy in order to react with each other. Okay, so two things that have to be true for collisions to occur. First of all, they have to occur with enough energy, and secondly, they have to occur with a favorable orientation. So let's talk about each one of these pieces. First of all, they have to occur with enough energy. Well, why do they have to have a certain amount of energy? If you recall the structure of an atom, you will recall that an atom is surrounded by a cloud of electrons, and electrons repel each other. So when you get one atom coming up to another atom and they try to get close to each other, the clouds of electrons are going to cause them initially to repel each other unless they have enough energy to go ahead and overcome that repulsion and go ahead and plow into each other. Okay, so they have to have enough energy in order to take place. So therefore, if I could increase the energy with which they're moving, that would give them perhaps enough energy to help overcome that repulsion. So therefore, if I increase the temperature of the mixture, then I'm also going to increase the rate of reaction because more of the molecules or atoms will have enough energy to overcome that electron repulsion and go ahead and collide effectively with each other. Okay. Secondly, they have to collide with a favorable orientation. If you look in your book at the bottom of page 347, he has a drawing here that will help to elucidate this. So let's go over that because I know sometimes students don't look at drawings in the book. They kind of skim over them. But this drawing is very helpful in understanding this concept. So right above, about 3 lines above this drawing, he has the equation for what is going on here. It's nitrogen dioxide plus carbon monoxide yields nitrogen monoxide plus carbon dioxide. So if you just look at the equation, what's going on? Well, I'm pulling off one of the oxygens, I'm pulling it off of the nitrogen dioxide, and I'm attaching it to the carbon to make carbon dioxide. So if you think about Lewis structures, you've drawn the Lewis structure for carbon dioxide enough times that you know that there's a carbon in the middle, doubly bonded to an oxygen on each side, okay? So therefore, in order for this reaction to take place, the carbon is going to have to collide with an oxygen in order to dislodge it and get it to bond to the carbon instead. So if I look at the possible collisions between this down in the diagram, if you look at collision A, the way those are oriented is that the nitrogen and the carbon are going to run into each other. That's not really going to be helpful. The carbon needs to run into the oxygen. In situation B, I have a nitrogen colliding with an oxygen. Again, that's not helpful. That's not what needs to collide in order to react. Situation C, I have an oxygen on one colliding with an oxygen on the other. Again, that's not where the bond's going to take place, so that's not helpful. And then situation D is where I am finally getting to a point where I have a carbon that's going to collide with an oxygen on the other one. That's where the new bond's going to take place. That's where the collision needs to occur. So of all the different ways in a mixture of gases, and remember, gases are moving, they're constantly rotating and turning, of all the different ways that these molecules could collide and hit one another, situation D is the only orientation where that collision is going to be effective. They may run into each other lots of different ways, but if the carbon and the oxygen don't collide with each other, if they're not the ones that make contact, then the reaction's not going to happen. And so that's why I say you have to have a favorable orientation. As these two guys collide, they're going to be, if you kind of would put that in slow motion in your brain, once they collide, there has to be a rearranging of electrons in order for them then to be able to separate into the new molecules that are going to be the products. that temporary union of the two reactant molecules where they're just kind of temporarily stuck together until they get all their electrons all sorted out. And they say, okay, you take these, I'll take these, now we'll go our separate ways. That is called a transition state or an activated complex, okay? It's very temporary, just until they get their electrons rearranged and sorted out, and then they will separate, okay? But I wanted to mention that simply because of the energy implications that are involved, which I'll get to in just a second. So kind of bookmark this in your mind, and we're going to come back to this, not only today, but also in the next lecture as well. So we already said that if I increase the temperature, I can increase the rate. What are some other things that I can do to increase the chances of not just a collision, but a favorable collision to occur? Well, one thing that I can do is I can increase the concentration, because this one should be a kind of an obvious one. If I increase the concentration, there's more molecules there to collide with each other. The more collisions that are occurring, the more chances there are that the collision is going to be favorable. So to increase the concentration is also going to increase the rate at which the reaction occurs. And that's something that we've talked about quite a bit already anyway. Okay. Secondly, I could increase the surface area, and it looks like my camera has slipped a little bit here, so you can't see the bottom of it. So if I increase the surface area, I'm also going to increase the rate. Okay, how is that going to work? Well, if you've got a big chunk of a solid reactant, the only place that the other things reacting with it are going to be able to make contact is on the outside of the chunk. And so there's going to be a limited number of atoms or molecules that it can make contact with. On the other hand, if you break the chunk up, you have a whole lot more surface area, and there's a whole lot more places then that those collisions can occur. And so then the reaction rate will increase as well. So I can increase the temperature, I can increase the concentration, I can increase the surface area. Another thing that we need to keep in mind are these graphs. Again, these are graphs that we looked at in your first year course, but these are graphs of potential energy versus reaction progress. And so hopefully you recall that if I look at this, my reactants are located over here and my products are located over here. And in this particular case, the reactants have more potential energy than the products do. And so therefore, the difference between the energy of the reactants and the energy of the products is going to be the delta H for the reaction. And so as you can see here, this delta H is going to be negative. And so that means this graph shows an exothermic reaction. Okay. Same thing is going to be true over here. Here's your reactants. Here's your products. And if I look at this difference, here is my delta H, but this time my delta H, if you take the final minus the initial, this delta H is going to be a positive change, and so this one is endothermic. Okay, again, this should be review. Here's what I want to look at. The difference between the reactant and this hump, because this is where your activated complex is. Okay, it'll be set over here, or your transition state. This amount right in here is the activation energy. Okay, and so over here, this one has a huge activation energy. So here's the activation energy over here. And so sometimes in order to get the reaction to happen more quickly, I just have to help it out in another way. A catalyst can decrease the activation energy that's needed for a reaction, and it speeds up the reaction. It can do this in one of two ways. It either changes the reaction mechanism, and that probably won't make a whole lot of sense just now, but it will after we talk about the last section in the chapter, which is reaction mechanism. So kind of, again, bookmark that. We're going to come back to that. or it provides a means for the reactants to get closer to each other. Now, this is the situation with what happens with a lot of biological enzymes. You probably studied this in your biology course, where you've got two reactants that need to get close to each other, but what happens is that you have an enzyme come in, the enzyme come in and hooks up to both of them and kind of forces them to get close together, and then the behavior of the enzyme acts in such a way so that the parts of the molecules that need to react with each other are then close to each other, and then they are able to react more easily. So it makes this favorable orientation happen much more easily. Okay, now this is usually one or the other. And so, see, this piece we're going to talk about the next video. So hang on to your hat for this one. Sometimes, though, reactions happen too quickly and we need to slow them down. And in that case, we use something called an inhibitor. And an inhibitor is the opposite of a catalyst. It increases the activation energy needed, and it's going to slow down the rate. So in general, you can say that a high activation energy usually indicates that you're going to have a very slow reaction, as you've got to have such an increase in energy for that to take place there. Okay. So, the other thing I wanted to mention was that really all of this stuff, concentration, not so much, but the surface area, the temperature, the orientation of the molecules, all that kind of stuff is all wrapped up in your rate constant for your reaction. So that's where all of that information makes a difference is in the rate reaction, because you probably looked at a rate reaction and said, well, the only thing in here is concentration, so how does this other stuff help? Well, the rate constant is going to change if the temperature of the reaction changes. The rate constant is going to change if you use a powdered reactant versus a big chunky reactant. So that's where all of this is included in your rate constant. All right.